Good morning. Welcome to Physics Studio. For today, you have today's a practice day. You have a right-hand rule practice sheet and a Pearson Access assignment plus a skill sheet, which is pretty simple. There are some challenging problems on the Pearson Access assignment, though, and frankly, the right-hand rule practice sheet, yesterday's classes struggled with it. So what I want to do is I want to go over a couple of the guidelines for reasoning and understanding these diagrams that we're producing. But the other thing is, you need to know why these are important. So let's start out with that, and then we'll just discuss some of the basic conventions and how and when you know which rule to apply. So if we have a charged particle sitting in space, right, we know there's going to be an electric field going off in all directions. Call that E. That's basically it. You know, it's just going to sit there, and by virtue of it being a charged particle, it's an inherent property that it has this field around it. Now, if another charged particle comes in the area, then some interaction occurs, but basically it's just sitting there. The thing is, if you put this thing into motion, give it some velocity, suddenly all sorts of things start happening. First of all, it's moving, it's got a velocity. Secondly, as soon as it does that, a magnetic field appears. And all three of these things are at 90 degrees to each other. You've got the field, the velocity, and the magnetic field B all at 90 degrees. That just pops into being as soon as it starts moving. And then finally, if there's a magnetic object somewhere in the vicinity, you're going to start having forces applied, so it really gets complicated. And what the right-hand rules do is they allow us to keep track of all this stuff going on. So let's take a quick look. Okay, first, a couple of things you need to know about the conventions for representation. Okay, number one, current goes from positive to negative. So whenever you see a positive and a negative sign, that's telling you the direction of the current. Number two, magnetic fields go from north to south. Now, really, this is actually going to be a bar magnet, you know, with the south pole over here and the north pole over here. But between these two, the primary interaction will be between them, and it can be quite uniform. You know, once we got outside, you'd start getting something like this, and then eventually this would loop around like that. This would loop around like that. But between those, we'd have a nice uniform magnetic field, and we'll call that B to keep it distinct from other vectors. Then number three, because we're in 3 dimensions, we need 6 possible directions. We have up and down, right and left, and these are the ones on the 2D surface of your paper. We also have into the paper and out of the paper. And the way you remember this is this represents an arrow, so when it's coming out of the paper, you see the point beginning to appear. When it's going into the paper, you see the crossed feathers disappearing. Okay? So keep that in mind. Now, right-hand rule number one is for a long, straight, individual wire. And we're going to determine the current of that by how we attach our terminals. So we can see here that the current is going to be in this direction, but it's going to follow the wire. It'll be tangent at all points. Now, right-hand rule number one just tells us the direction of the magnetic field around that wire. And you put your thumb in the direction of the current, wrap your fingers. So on this side of the wire, the field's going into the board. This side of the wire, the field's coming out of the board. So into the board, we're going to represent by X's. And out of the board by O's. And that field continues out into space, right? It doesn't just stop there. And so if we brought a little magnet inside this field, it would be governed by the direction of the field at whatever point we put it. And we will label that B, so we know that this means the direction of the field and this is the direction of the current. Now, right-hand rule number 2 is for when you have loops, multiple loops, or a solenoid. Right, when you configure this long straight wire into a bunch of loops, we get a certain behavior. Now, what's going to happen is you're going to be tempted to apply right-hand rule number 1 to this, and you would not be wrong to do that, but something else happens. So let's just put some current in here. We'll put the positive terminal here, the negative terminal here. So the current is going up here, around here, and then out here. Now, if we applied right-hand rule number 1 to anywhere in any one of these little loops, right, these single loops of wire, we'd get a little magnetic field circling it like that, right? But we know from gravitation and electrical fields that if you have multiple fields acting at a certain point, you just add them up. And so right-hand rule number 2 gives us the resultant field, the big field, because all these fields are going in the same direction. And what it tells us is if we wrap our fingers in the direction the current is physically looping, our thumb points to north. And I've put an iron core through that to make it an electromagnet. Now, because this is a north-south field, this is going to behave a lot like a bar magnet. And we know that the field diverges out of the North Pole and converges and dives back in at the South Pole. And so that is our magnetic field around there. Now, you will be tempted to want to say, well, maybe positive is always associated with south and negative is always associated with north. That's not the case. If you wrap the loops in the opposite direction but kept the positive terminal here, the North Pole would jump over here. Conversely, if we switch these two and make this positive and this negative, then the North Pole suddenly appears up here. But the point is that plus and minus are independent of north and south. They're mediated by the direction of the rat. So don't associate them directly. Now, last thing is right-hand rule number 3. And that's the toughest one. And I won't belabor it, I'll let you figure it out today. But right-hand rule number 3 is for when we have an external magnetic field and a moving charge. And the question is, what kind of force does that external magnetic field exert on the moving charge? So if we have, say, a north here and a south here, and we know that this is actually a bar magnet with an end. Got our field going this way. And we'll call that B. Let's say we run a loop of wire through there that's free to turn. Give it a current. So current's going that way. Let's mark 3 points, A, B, and C. We can see at A the current's going to be going up, right, just following along. And we apply our right-hand rule, which says that if you put your thumb in the direction of the current, your fingers in the direction of the field, the force comes out of your palm, which means this part of the wire is being pushed down into the board. So let's imperfectly represent that like that. There's another version of the right-hand rule in which you put your fingers in the direction of the current and then you wrap your finger's in the direction of the field, your thumb indicates the force. But again, we get the same result into the page. Now, if we apply that over here, thumb in the direction of the current, right? Because the current's going around, and now it's coming down, physically down. Fingers in the direction of the field. The force comes up the palm. In other words, the force is coming right toward you. We'll represent that like that. Now, you can see that what's going to happen is this is going to be pushed and this is pulled and it's going to spin this thing. Now, up here at B, though, an interesting thing happens. The current is in this direction, and the angle between the current and the field is 0. And we know that the force equals field times current times the length of wire times the sine of the angle theta between the movement and the field. And the sine of theta, or I'm sorry, the sine of 0 degrees equals 0. So the force at point B is 0. That current's moving along there, but there's no interaction between the fields. Now, when these two things flip up to here, they're suddenly traveling parallel to the field and the force drops to 0. But inertia will push them past there. Question is, what happens then? And that's the subject of one of your Pearson questions. All right, now, the other thing, and this is relatively simple, but if we want to know what's happening with a moving charge as opposed to a charge confined to a conducting wire, we have an external field B, in this case going into the board. Let's say we have an electron. We shoot that thing into that field with a velocity v. The right-hand rule is going to tell us the force that it feels. And thumb goes in the direction of the velocity, fingers in the direction of the field, force comes out of the palm. So that means a proton would experience force upward. That's what the right-hand rule tells you. Since this is an electron, it's going to experience force downward. And that will be a key to one of the Pearson problems. So I hope that sets you up to succeed today. Do your best, post your answers to, I've got a questions parceled out so that we can produce a key. So let's see that appear over the course of the day. And good luck, and let me know what's going, or if you have any questions, raise them in discussion. See ya.